All right, good afternoon. How you guys doing? All right, I know many of you, perhaps not every single one of you, and you probably don't know each other. So, first of all, hello, I'm Samuel Snow. Um, I'm a faculty in environmental engineering, of course, do water and wastewater treatment, usually on the physical chemicals treatment technology side of things. So that's why I'm here teaching the class. I've taught this class a few times before. Sometimes I've taught it and felt like I didn't really organize it very well. I think last time I corrected it, so I think this time it'll feel a little better. So I'm going to introduce a little bit of that, what to expect about the course, take a look at the syllabus with you, kind of just talk about general expectations and share a little bit about how the course, how you can expect it to go. But perhaps before we get to all that, why don't we go around and share a little bit about yourselves? Name, kind of what your research or area of interest in particular is. And that way you kind of get to know one another a little bit. All right, want to start?
My name is Isabel. I have a master's in coastal sciences. I studied marine molecular microbial ecology. You probably would like my thesis that I did. It was on a recirculating aquaculture system that
cool.
reared oyster larvae. And I
Okay.
studied the microbes that lived in that aquaculture system. But I've switched over to environmental engineering.
Great, great, interesting.
I'm from Nigeria. I'm a new student under Professor Mowis.
And what was your name? Farron.
A new student under Professor Mowis.
Okay. And what are you studying or plan to specialize in?
Chemical engineering.
Okay, gotcha.
I'm Shabur Bishen. I'm a master's student here. I joined last spring. I work at Dr. Bean's lab, and I'm currently working on inovirus HAV virus, and I really, I would really like to work on wastewater treatment systems someday, and my uh, that's my interest.
Thank you.
Hi everyone, I'm Dev. This is my third year in PhD in Environmental Engineering, and I am working on wastewater treatment.
We'll just go around the back.
Hi, I'm Monna. I'm in my second year of my PhD journey in environmental engineering. I am basically doing the household wastewater treatment plant related microbial pathology related work. That is my PhD research. That's it.
Thank you.
Hi everybody, I'm Dilruba Akhtar. I'm also in the second year of my PhD in Engineering Science program. I am doing my research in natural and nature-based solutions, so that's why I think this course is quite relevant. Thank you.
Thank you.
Hey everyone, previously attended and graduated in fall 2020. Back here for a non-thesis master's. Interested in groundwater remediation, models, stuff like that.
Great. Welcome back.
Hi everybody, my name is Samtu. I'm in the second year PhD, also in chemical engineering, and my research is focused on photocatalytic wastewater treatment.
Thank you.
Hey everyone, I'm Evan. Doing my PhD in environmental engineering. Working with microfarming and business lab.
Either way.
My name is Sydney. I am in my second year of my master's program, and I'm doing coastal and ecological engineering. And my thesis is on microbial communities treating groundwater contaminated by VOCs, and they're being filtered through an activated carbon vessel and like a superfund site.
Cool.
My name is Abby. I'm also a second year master's student in coastal ecological engineering. My thesis is on like the biodegradation of like legacy oil leftover in the Grand Isle area.
microplastics and how they're removed from the environment by wet zones.
I'm Maddie. I'm second year master's environmental engineering. I work for Dr. Snow, and my research is quantification of hydroxylamine with the entrance of wastewater pollution.
My name is Michael. I'm a second year master's student in environmental engineering, and my thesis is on biodegradation of amines used for carbon capture.
My name is Leah. This is my first semester of my master's in environmental engineering, and I'm also doing a non-thesis master's.
All right, thank you all. I realized I probably should have asked for like embarrassing stories or something to kind of lighten the mood on the Tuesday afternoon. maybe we'll get there next time. Okay, well, thank you. I don't have any specific plans for like group activities or something, but I think if we do find something, I'd encourage you guys to work with one another. It's maybe a good opportunity to rub shoulders with people who you don't normally encounter. For a grad class, this is actually slightly bigger than normal, so I think that's pretty cool. All right, so coming back to the class itself, I like to give just a very rudimentary overview of what we're doing and kind of start with the big picture. So if a few of you have actually taken my classes more than anybody else, just this one little set of students here have just followed me along. The only time I taught eVeg 2000 was that time for you guys, and it's been since. So a few of you have seen a lot, and you've probably seen this a lot, so sorry if you're bored of it. But we're just going to start big picture. By the time we're in the next lecture, we're going to be into some much more technical type of stuff. But today will be a kind of a bigger overview and kind of show you what I plan for the course. So what I like to say is pretty much any part of environmental engineering is really about taking some stuff that's in some media, so stuff in other stuff, and transforming it, separating it, or destroying it, or doing something to it. And we could easily visualize that in the case of water treatment, which is kind of the focus. If we have some water, we send it through some process here in the middle. Could be biological, could be chemical, could be physical. And usually what we want is to either destroy or to separate it, so maybe we'll have less of the bad stuff in our water and a little pile of the bad stuff on the side, right? We could landfill that, we could contain that, we could burn that, whatever we're going to do, we've accomplished in this case a separation. Maybe we're just eliminating it, or maybe we are causing a reaction so that these living organisms no longer could multiply or live or whatever. So there's all sorts of ways we could think of this, but in general, what we are after is how to design a process to accomplish that goal, right? So as we are thinking about an adsorption process, we're going to send some water through our adsorbent, and what we're interested in is finding the math that tells us how much stuff can adsorb to the adsorbent. How much adsorbent do we need? When do we need to refresh it? All these pieces to understand that part of the puzzle to achieve our end goal, right? So that's ultimately kind of the direction we go. The book that we will take a look at, and I'll bring up the syllabus in a moment, show you that. It's organized, so if you take a look at it, you'll find it's organized into kind of 4 sections. There's reactors and reactions, there's removal and transformation of dissolved constituents, then there's removal of particles from water, and then there's membrane processes, which overlaps a lot with removal of particles from water, but it also interacts with removing dissolved stuff if you go fine enough of a membrane. So with all of that, it's kind of too much to cover in one semester, I've found. So we're going to focus in, of course, we're going to kind of talk about reactors and reactions, and then, well, let me just go ahead and pull up the syllabus. We'll show you. Since I also sometimes teach, or our department teaches, something that focuses a little more on the chemistry side of things, I'm going to gear this one a little more towards the physical processes. things like adsorption. So you'll see our plan kind of is to go through reactions, reactors, going from there, and that'll be kind of our first segment is understanding almost the container that we accomplish some transformation in, and that transformation process itself in terms of how quickly do things happen. That's going to be the focus of the first unit of our course. From there, we'll talk a little bit about gas transfer, some fundamentals there, and adsorption. Turns out those two are fairly similar concepts in terms of adsorption models often are used for gas phase type of stuff, but adsorption is also used in the liquid phase, and we'll get into a little bit of colloidal principles in terms of colloids adsorbing and surface chemistry with that. The last segment then will be on more chemical transformation, chemical removal type of things. So this is my plan right now. If you give me some feedback on the early side, I could shift this. So if somebody really wanted to learn something in particular and felt like you'd really love to have a course on something, you're welcome to speak up, and I'll see what I can do to adapt. So if we take a look back at the slide I had. So in that sense, of course, we're going to do some reactors and reactions. That puts us in the context, what we're doing. If we say this is a second order reaction, what does that mean? What implications does that have? And what might be the best reactor to put that in, right? There's a lot of things we can consider with that. So then we're going to take kind of a physical approach to some dissolved and a chemical approach as well to the dissolved. We're not really going to touch on membrane processes too much. I do have a few lectures on that I could share with you if you're interested. In the past, we had a 4,000 level special topics course on membranes, and we just hired Dr. Se-Woon Kim, who's also a membrane specialist. So he will probably teach that or something similar pretty soon. So if you did really feel like you needed some membrane stuff, you can let me know. But there's probably going to be some good opportunities for courses dedicated to that. So it's probably not going to touch on that too much, but I'm sure I'll mention it. Okay, any questions so far? Okay, we will go through the entire syllabus, and in a way, I guess that's kind of what my slides are doing anyway. Okay, so the book itself, these chapters, it even tells us how to use the book. And one time I didn't listen to it, and it was a bad semester. I didn't like that. So I'm going to listen to this book. It says, listen to the text. It says, yeah, it's too long. Material in part 1 is covered in greater depth than is done in most curricula, but it still can be covered in depth with approximately 4 to 5 weeks. So it goes through all the different parts of it, and I'm showing you this in case you want to use this as a reference for something else, right? If you decide, all right, cool, I learned some things in this class, but I actually needed something else. Well, take a look here to see if, if you need to use this for some research project or for something in the future. It'll be good knowledge to have this as a reference to say, oh, okay, here's that book. I am recommending that you get it, but I'm flexible in terms of, let's see, I'm trying to remember. Can't remember if I've assigned specific problems. I think you probably need it for I'll give you a problem to say, hey, go solve this problem. So I am asking that you get it. If you're doing anything with water treatment, you're going to be glad to have it, physical or chemical processes. It is a thick book, and I believe there's an online version. In fact, I think if we go back to the syllabus, I think you could even check out one copy at a time maybe, but you can check out the book from the LSU library. So it might make me log in, but so if you use this link when you're on LSU's campus, I believe you can get the full text like that. So hopefully it's not a big deal. You might want a physical copy. So take a look here and figure it out with the library. I don't recall exactly all this, but that at least gives you the information of what book it is and where you can find it. Okay. There are a few other books that you might take a look at. Okay, so we have that tentative schedule. I'm probably going to design some sort of a feedback activity for our next class Thursday to kind of get an impression of how you're feeling about the different topics. I didn't prepare that for today, just was keeping it pretty simple, but that'll be something where you can kind of write a few notes like, hey, I'm really uncomfortable with this, would really like to see that, that kind of thing. All right. The overall structure, assignments and things, my plan is to have two exams, 2 midterm exams and 1 final. That kind of splits up the course material a bit, with a homework assignment associated with each, kind of on that particular topic. I've also decided to cut the reviews down to just 1. So what I'm going to have you do is during the semester, as one other assignment, is to write what I'll call a critical review. And the assignment will essentially be to find a paper, a peer-reviewed journal article, and critique it. This will be a little bit like a journal club activity, but it'll be your own perspective on what's good and bad for this article. Did they really support their claims with the evidence? So it might be a good idea to find a bad paper, easy to critique, right? But it will. What I'm looking for is for you to use your own study to see, okay, are they just repeating somebody else's work? Did they do something new? Is that new thing actually important, or are they overhyping it? Give a critical eye to it. Maybe you find a really great paper and it shows because a lot of people are citing it and you can't find anything at all wrong with it. But what you could do is talk about, well, nobody else did this first, and so that's why it's making a big impact. So this will be an assignment to really give a critical review, and we'll talk more about that. I have kind of a rubric for you for that. Okay, textbook is here. Another thing that I do, which I hope will be useful for you, is I'm actually live streaming right now. So I live stream our lectures. That means they're recorded, they'll be saved. Assuming I have all the sound things in order, we could go to this page and find some Inception, basically, which I'll just pull up a browser for that. In Moodle, you'll see a link to it, and if you go to my page, you'll see that we are currently live right now. I just post my lectures here. There's maybe a couple other little things. I will sort everything or put everything into a playlist for our class. You can see some of the past classes here, and there will be, as soon as I add a video to it, it should probably come to the front. This one will go there, and then you'll see our, but I've already made one, it's just not showing. And so you could show up right here, and if I had my sound on, you'd hear me again, and again, and again, and again. So that's all happening. So if you ever have to miss, if you're sick or something, you can catch up that way. I do appreciate you being here in person, so I can get to know you, get to know one another. But if you travel for a conference or something, have something that comes up, let me know about your absence, and you'll have resources to make up. Okay? So that's the deal. It's a resource for you, convenient for me to have it there, and I'll also share the slides and everything, which is also why I have the little glove thing, so I can write on my little tablet, and it's convenient that way. So this is kind of how you'll find the class. I'll write equations and stuff here, and I can erase it, but I'll keep the notes that I make and post that for you on the slides. And on Moodle, I don't know if I pulled up the page. In Moodle, I will post the blank slides before class and then fill in with the filled in slides later. So I don't know if I did that today, probably not, but in the future I will do that for you. Okay, just a little bit more about the context of our course. Well, first, any questions on that? I guess I need to finish going through the syllabus. So grade-wise, so I don't skip over this, 2 exams plus the final, so 3 exams. Homework assignments, probably 3 total, and the average of those being 100 points out of 500, and your critical review being an additional category worth the same as an exam. So essentially 5 grade categories. That'll make your total grade. Pretty self-explanatory for all of that. Okay. So I think that about covers the syllabus. Any questions on that? Anything you guys feel like you want to see or are scared of? Or I'll get more feedback from you on Thursday. I'll make you write a little bit.
What is the exam like?
Very hard. No. It should look something like the homework, but scaled. So the homeworks from this book, by the way, they're pretty intense. So sometimes if I don't scale them back well, you probably need the book, and it'll probably go well beyond the course. And I'm going to try to bring the exams back towards more from in the course, but that means we're going to be applying what we learned in the course, let's say a mass balance, perhaps to a new mass balance you haven't seen, right? So it will be from a little more directly related to the course. For example, a homework, maybe we'll talk about a particular equation for a tracer test that we just glossed over, mentioned it in class, but we didn't solve anything with it. If we didn't solve anything with it and we only just mentioned it and it's on one slide somewhere, I didn't even spend more than 30 seconds on it, that's the kind of thing I'm going to aim to not include on the exam, that you know something important about that and that's the crux of a problem. Now, there might be cases where I say, okay, well, you could apply this to something else that we only mentioned, but you already have the knowledge for it, right? So you can apply the fundamentals to this other situation. That would be fair game, whereas expecting you to know the fundamentals of some other concept that we didn't really cover. So I'm going to aim to scope it so that there will be a little bit challenging, but certainly manageable based on what you learned from the course. That would mean typically maybe a few questions that are a little more topical, maybe true, false, or multiple choice, and then a few where you're solving problems or writing a statement on, okay, how does this work? So I'll better prepare you. I'll use the homeworks as a time to touch base with you to say, okay, what are we still missing or whatever. Go through the homework solutions with you as a kind of exam prep. Sound good? All right. Okay, so water treatment. We want to talk about both water and wastewater treatment. And as we do so, the criteria for what we're trying to accomplish depends on the context of what we're trying to do. For drinking water, of course, there are different standards than for wastewater, right? We could discharge wastewater in a manner where there's not really going to be any human exposure to it anywhere nearby, and maybe that's okay to have some pathogens in it, right? Maybe there's some amount. Maybe we try to reduce it by a certain amount, but we are okay with a certain amount of pathogens. Now, if I were to ask you, do you think there are any pathogens in here? What would you say? Yeah. Okay, we got a yeah. Anybody? And let's assume, this is a false assumption, but let's assume I cleaned it very well this morning and then filled it up from the water fountain and haven't drank out of it yet.
Everything is everywhere.
Okay, we got some everything is everywhere. Anybody have more faith in our water treatment? What if this was a water bottle? like a unopened water bottle, like a fresh from Dasani or whatever. Still? Anybody else? Okay, our microbiologists are cutting to the chase here a little bit. Very likely, there are some pathogens in here. And I'll drink a lot for effect, right? The thing is, there's a difference between an organism being pathogenic and being capable of infecting you. For many organisms, it takes many of those pathogens on average to get by your natural defenses and form an infection and cause trouble. So now, maybe when I say pathogens, that's too broad a term. Maybe I should be saying human pathogens, because certainly there's very likely some organisms that are pathogenic for other organisms, like maybe some viruses that infect algae, for example. And for sure, there's going to be all sorts of random stuff in here, and I didn't clean it this morning, and I have been drinking out of it. So whatever's in my mouth and whatever might be pathogenic or whatever, it's going to be around, right? So there's going to be stuff. So when we say disinfect, what we're talking about is not actually sterilizing, completely destroying or completely preventing anything from being able to multiply. What we're talking about is removing so that we are no longer at an infectious level. So if there was one Vibrio cholera bacteria in here, and you could promise me that there were exactly one and it was alive and healthy, I would actually have fun drinking the whole thing just to make sure I drank it, because it's funny. Because one cannot make me sick. For that particular organism, we know that it takes something on the order of 10 to 100 million of them, and all the more if you have an empty stomach and a lot of stomach acid. So, if you told me there was many and I must drink it, I would wait until I was very hungry, have a lot of stomach acid, and then I'd have better chances of not getting sick. So anyway, all that to say, how do we decide on our treatment standards? Well, the first and most obvious one is health standards. We want to make sure that our water is safe to drink, right? So these, at least for the US EPA, these would what we would call enforceable. So these are the primary or enforceable standards. And we have aesthetic standards, meaning, or also called secondary standards. And these are actually not enforceable. They are recommended, but not required. So how many of you would like to drink some brown water? Anybody? Nobody likes to drink brown water? I mean, I think some of you are lying to me. Like Michael over here is sitting with some brown water on his table. I think he likes to drink it. I don't know why he'd buy it if he didn't. So I don't know. I think some of you are full of it. How many of you enjoy tea or Coke or beer or, maybe wine, red water, or whitish, or, not white, but like off yellow, something. So as we start to think about it, it's like, oh, okay, fine. Some of these things, the water is okay if it's colored, if I call it tea, right? So we can think of aesthetic standards in that manner. There are things that we are okay drinking that look like they might be a problem if we were expecting the water to be nice and clear and pristine, right? So obviously there's some things that could have no health impact, or maybe let's imagine a positive one. Let's say tea might be good for you, right? Perhaps a good health impact, but if it was coming out of our tap, we would not want it, right? So that's some of the context this applies to: taste, odor, and sight, but also things like hardness. So if your water causes lots of minerals to precipitate, hard water also is harder to remove from it makes soap less effective. And if it's super, super soft water, it actually feels like it's hard to get rid of the soap off your skin if you're like showering with it. it's strange. So there are some aesthetic standards to say, okay, we would like our water to be this type of stuff. Even oxygen content. If you didn't know, oxygen actually makes your water taste a little better. So if you've ever had like water that's been sitting in the sun, it's like 90 degrees, and you try to drink it, and it's like, ugh, right? Part of the reason it doesn't taste very good is it has less oxygen than cold water. It just holds less. So there's some things like that where our physicochemical processes here directly play into what's going on with our water and whether or not we're going to enjoy it and like it. So that's on the drinking water side. On the wastewater side, the primary motives are to protect intended uses. What are we using this lake or river or stream for? What would we like for it to support in terms of ecology, in terms of recreation, all of these sorts of things. And at the end of the day, rivers should not be flammable. That sounds pretty self-evident, but it's happened in the past. So maybe we'll take a look at examples. So turns out if you don't regulate discharge of grease and industries, this was kind of, I guess what now we kind of call the Rust Belt. There were lots of industries that were not very careful with recycling their waste or capturing it. They would discharge a lot of it. Well, turns out oils and greases tend to float on water, and if you discharge enough, you get an oil slick on your water. And add some sort of ignition source to that, and suddenly you have a big grease fire on your river, and how do you put that out? Do you guys know how to put out a grease fire if you had one at home? Or at least what not to do? Don't put water on it. Why?
Because the oil and the water don't mix, and so the ignition source, the oil or grease, is just going to disperse.
Yeah, and so the reason it disperses is because water would like to be below the grease, right? And so water's going to sink, and the oil will float. The oil is the thing that's on fire, right? So what happens is if you put water on top of the oil, there's going to be some inversion there, and the oil is still super, super hot, has a much higher boiling point than water. As soon as it has done this number, if that has not already splashed burning oil everywhere, well then what happens to the water is it's going to boil, but it has nowhere to go. So it is kind of a small explosion to spray that burning oil everywhere. So don't use water to put out a grease fire, is the point. So if you have a grease fire on a lake, how do you put it out? You hope the wind blows the other way and doesn't get your boat, right? Or your dock or whatever, right? And you probably have to let it burn. That would not be a fun situation. Okay, so some obvious reasons for wastewater treatment, and of course for whatever we need to remove from that wastewater, the particular contaminant often tells us or informs us about what kind of treatment are we going to want, right? It looks a lot different to remove oil and grease. Actually, it's a very simple physical process because it floats, compared to removing some trace organic compound, right? It might also be a physical process, or maybe we could use a chemical process. I mean, you could burn the oil, that's a chemical process. So we could do oxidation events that way. But at any rate, this will, where we land in terms of what we're interested in kind of defines what kind of treatment we need. In light of that, we also want to think about, in general, the water cycle. It's an important component here just to think about, okay, what water source are we treating or are we discharging to? And how clean do we need to make our discharge or our intake, right, before we are drinking it? So all of that plays in to what we're dealing with. This is an example a long time ago. It's kind of I think I didn't grab the high resolution version of the picture whenever I copied this over. But this is a water storage tank in Nicaragua from one of my first trips there a long time ago. And people had this nice piped water to store it, to use it, but they would store it in these bins, and then it's open to the environment, and you can see leaves and things, and we've tested things like that, and it gets pretty dirty. Who knows what animals might be using that to bathe in or to drink from at the middle of the night or whatever. So it gets recontaminated, but was otherwise fairly clean drinking water from a groundwater source. So maybe it wouldn't be hard to treat that again, but ideally we'd avoid that altogether. So this is the kind of stuff, that those two are just kind of painting that picture of how do we treat the water, what are we treating it for, and how are we protecting it along the way. All right, so when we think about the human side of the water cycle, we can look at this little figure from, this is a kind of a more introductory textbook, and we can look at where all do we touch it and where all do we get it from. So we tend to take water for drinking from one of three places. One would be maybe a reservoir. Another would be like a lake or a stream. Both of those together, maybe we call those one and the same, surface waters. And the other would be groundwater. So we're going to pull it up from a well. Of course, there are perhaps other options. We could do some desalination and use ocean water or some brackish estuary water. Maybe you could harvest some water from the atmosphere if you do some sort of a dehumidifying type of operation. And if you're on the space station, where do you get your water? It's a question for you. Where does the water come from? Urine? Yep, your waste, right? And more than just your urine. There's moisture other places too, right? It's expensive to ship a bottle of water to space. Let's just say that, right? I think it takes something like 1,000 times the mass of fuel as mass of water or something. There's a huge ratio of fuel required to get 1 kilogram or 1 pound up to space. So so in some cases we could perhaps do complete recycle, right? The good thing is we have technology that can accomplish that. And then the question is, what is the cost? What is the cheapest way to assure that we are getting the water quality that we need with the appropriate safeguards, right? That's kind of the deal at the end of the day. If we're taking from a stream or a reservoir, there's potentially lots of animals around that could be adding their droppings to it. So maybe even if there was no wastewater treatment plant upstream, well, we can say at least there's some animals that are contributing some potential pathogenic waste. It's typically, our typical concern is other animals or other humans that are warm-blooded, that have warm-blooded guts, right? So a fish excrement is a lot less likely to contain human pathogens than a pig, because the types of pathogens that can grow in our stomach are going to thrive in warm-blooded guts, and fish are not warm-blooded. They're going to just be whatever temperature the ambient water is, right? So it's there's a big difference there. So we could think about, well, if we're taking groundwater from a well, if it's deep enough, it might be far enough separated from any pathogen that there's not a whole lot of risk. So maybe we just do a little bit of residual disinfection to make sure it stays clean through our system. Maybe a little bit of a shock just to be sure anything that was there is dead. But it's a lot different treatment than we might need if we were taking, let's say, directly from the Mississippi. And that's actually the difference Baton Rouge takes from a deep groundwater well that's a nice aquifer. And New Orleans doesn't have access to fresh aquifers, so they take from the Mississippi. So their treatment needs are much different than ours, right? Okay, so then we send it through the distribution system after doing our drinking water treatment. We send it through, and maybe some industry takes some of it. They're going to make their own particular type of wastewater. We're going to use it in our homes and things like that. And we're going to make what we typically call municipal wastewater. So if we have industrial, that might take some special considerations. Maybe there's some really hazardous chemicals that we have to treat in a particular manner. Regulatory-wise, usually there there would be some sort of pre-treatment step required if they are going to add the rest of their discharge to a municipal sewer system. It's possible, but they can't discharge something that's going to kill all the microbes in our wastewater treatment plant, right? Even if they're paying the wastewater treatment plant to take their water, if the wastewater treatment plant can't handle it or couldn't handle a pH spike or something, they're not allowed to do that. That's just going to be a no-go. So they'd have to do some pre-treatment. From there, whether or not we have got the industrial, and sometimes industrial looks the same, let's say a paper mill might have a lot of carbonaceous, carbon-rich waste, and you would treat it with a biological reactor a lot like we would for municipal wastewater. The only difference is it's very starved for nitrogen and phosphorus. So I actually visited one time a tissue recycling plant, and they would literally just add gallon things of fertilizer, nitrogen and phosphorus at a particular ratio, just fertilizer like you'd use to fertilize a field, right? And they'd add X number of gallons per day to feed their microbes. And they had all the carbon they needed, and so they were just adding it to take care of that waste, to allow the carbon to be transformed into cells, which you can separate. So that's kind of our wastewater treatment process. We're not going to go into the biological side of that. There are courses on that. Probably a lot of you have seen that or will take them. Maybe they're, what is Dr. Mo teaching right now? Is he teaching a wastewater? He just taught one? Anybody? Not teaching it right now. Okay. Yeah, so he teaches a grad level wastewater class. So if that's what you were really here for, we'll touch on the physical and chemical sides of it, but if you wanted the biological side, you can take his class. Okay. At any rate, then we discharge, and depending on where we discharge it, again, that might be a factor in terms of how clean do we need to make it, right? Are we on the space station? Maybe we are in a desert and want to repurpose it as much as we can. Maybe we've got the Mississippi River and we don't even need to dechlorinate because the Mississippi River doesn't care. And that's just the way it is. So all that depends. Okay, one thing to kind of highlight water and wastewater treatment, if we take a look at the rate of typhoid fever and the death rate from it, I think this is in the US. According to the CDC, we used to have 20 plus deaths per 100,000 people every year from typhoid fever, and we kind of began chlorinating our drinking water sometime around 1910. So this correlates really well with that. This is not strictly the only thing, but our wastewater treatment was also improving. Our health, systems, healthcare in general was also improving. So the combination of all these things certainly brought typhoid to basically no deaths anymore. Now, the reason I'm highlighting this is because you probably have heard of typhoid fever, but it is a waterborne disease largely. It is food or waterborne. It is a fecal oral route of transmission, meaning if you get typhoid, you've ingested something's excrement that had typhoid bacteria, right? So Salmonella typhi, right? So all this to say, this is a great protective mechanism to have appropriate water and wastewater treatment. Okay, I mentioned hardness earlier. So again, just sticking with kind of the big picture, why we care about this stuff in the class. If you take a look at this map, what we're looking at is how hard is the water, how much mineral content. This is largely going to be calcium and magnesium ions. So depending on where you visited, where you grew up, and a lot of you may be from some other countries, some other places, it varies, right? The geology itself, the mineral content in the ground, that's going to be what dictates the hardness of your water. So I grew up in this area over here, a little north of Atlanta, and now I'm experiencing water here. I've also lived briefly up here in Michigan, and you can kind of see, all right, there's some big differences there. When I was in Michigan, it was definitely harder water. And certain places in Louisiana, we do end up with hard water, but a lot of it's rather soft. So any of you ever notice this? You know what I'm talking about when I say the soap acts differently? Any of you have no clue, never experienced? Some of you just ready for the day to be done? Okay, so you might notice it as we go. We spend a fair bit of the time. I taught last year a course with the chemistry side of stuff. So if you're interested in softening and some of that, we'll probably talk a little bit about it in this course, but I have other materials if you are specifically interested. But again, just to show where we're getting our water can tell us how we need to treat it. Our class itself is going to focus on, okay, given some situation, how do we treat it? What do we need? But a lot of these things, it'll depend on the inputs that we have. Okay, so last thing I want to kind of touch on is a big picture look at a typical drinking water treatment plant. And I'm doing this so that we can kind of get a sense for the different processes we'll be taking a look at. And we'll find specifically the physical and chemical processes in many of these in the drinking water treatment. A lot of these could be used in wastewater as well, like we will do sedimentation. We'll typically call that the clarifier, but it's physically pretty much the same process. So in a typical surface water treatment plant, again, this will be different if we have a groundwater system. We would have some very, very basic physical barriers to remove any basketballs floating in the water, any fish that might try to swim in, whatever, so like a bar rack screen type of thing. Then we would probably also have what we might call a grit chamber, get rid of any sand and heavy but small particles that could really damage the pumps and things within the system, something that can be removed rather rapidly. Then send us into primary sedimentation. Now that's going to allow any large particles that were still suspended but could easily fall out of solution to do so, right? That will let some things be removed, and we're going to take that into some sludge processing. There's a good chance this will go into some kind of dewatering, producing some wastewater, and some solids that we could landfill, something like that. So that would be primary sedimentation. From there, and we do that because we want to use gravity. It's very convenient, very cheap. We just need some space to let it settle. From there, we're going to do a couple things that enhance that gravity to make that happen, but better. So we would add some coagulant. It's going to cause small particles that we missed. They were too small. They might have been falling just too slowly to make it out. We're going to add something to accelerate that to cause them to stick together. And it turns out that if we cause particles to stick together, the physics, the difference between the buoyant force versus the drag force versus force of gravity and all of that, it turns out if we just cause the particles to stick together, they will fall faster. So if we can cause them to stick together by adding something that effectively makes them sticky, we'll talk on the technical term about that in a little while. That's our coagulant. Then we give them some time to stick. That's our flocculation, gentle mixing, allowing the particles to meet each other. Then we do sedimentation again, and it works a lot better. We get a lot of more stuff. Sometimes we even add minerals that then precipitate. And so we are adding this chemical and then causing it to precipitate, and we get precipitates as well. It's going to add a bit of sludge to process, but it's going to be worth it because we capture so many particles, and it's very simple, and it's a safe way to get rid of many, many particles. Now, for whatever happens to be left over, we almost always do some form of filtration after that. So that could be something as simple as granular filtration. We'll talk about that. That is not necessarily size exclusion. It's actually more like an adsorption process, allowing particles to stick to sand grains, and then we can design that accordingly. And from there, we would likely disinfect. Maybe if we're doing some water softening process, we'd probably add that here. We could also add any advanced oxidation process or things like that. Would also go in that kind of same spot. Before disinfection, after the water's been polished up pretty nicely, particles could hide bacteria or viruses. So if we get rid of all the particles, the microbes have nowhere to hide. Right? So if we're using UV, there's no shielding. If we're using chemicals, there's no sort of protective coating they could end up having around them. So if we think about a particle, it might be that there are bacteria literally inside the particle, kind of in some space there or something. It might not be as simple as a ball with something sticking on top of it, right? So whatever the case is, we want to clear out the particles. That takes out a fair amount of the risks and makes anything left in solution more vulnerable to our treatment for disinfection or any of that. Okay, so that's kind of the scheme. From there, we would go into distribution systems, and we generally manage that as if it were a part of the treatment process. So that would be typical for a drinking water treatment plant. And we might, okay, I do have the wastewater. So you see there's lots of physical processes there. For a wastewater treatment plant, this would be a typical municipal plant with primary and secondary treatment. We do have some biology happening. Again, we're not really focusing on that in this course, but one thing that would be relevant that we probably will talk about is how are we doing the aeration there? How are we adding bubbles in a way where it's going to oxygenate that system properly for our procedure? So you'll see, again, we have sedimentation, and a clarifier is typically what we would call this. Then we'd have our bioreactor. This is something to allow the biology to munch on all the dissolved stuff and transform it from dissolved molecules into particulate cells. So now we have cells that we can physically remove better. Then we'll sediment those, capture them, do some fancy recycling stuff to keep the microbes happy, and process whatever other sludge we are wasting. From there, we would probably disinfect and discharge. So we might have some dechlorination if we're using chlorine. So at the tail here, maybe we add, a lot of times we add something like thiosulfate or some reduced sulfur form. Takes a lot of electrons to convert it to sulfate. And so you don't need a whole lot of reduced sulfur to get rid of all your chlorine that's going to oxidize it. So maybe we dechlorinate here. If you were being fancy on the biological side, you would add tertiary steps here for maybe nutrient removal. So you could do that. So in any of these systems, you can always tweak things, add things, change things, design it differently. Doesn't have to be an aerated system necessarily. Maybe you have some anaerobic system and an aerobic. Maybe you have a membrane instead of the sedimentation, and it's called a membrane bioreactor. Maybe you add some advanced oxidation if you're worried about discharging some pharmaceuticals into the environment, right? So again, we'll talk about it more during the class, but sometimes you might consider, and I think Switzerland is, I don't know if they've mandated yet, but they were working towards applying advanced oxidation to all their wastewater in hopes of keeping out pharmaceuticals from their natural waters. And so you'd put it maybe after disinfection or maybe right before. It doesn't matter too much for that. Okay, so that's kind of a big picture overview of the types of systems we'll take a look at. We're going to probably zoom in on different components. We'll probably talk about some things that it maybe doesn't even quite feel like it fit in either of these. For example, if we had a leaky underground storage tank from a gas station that was leaking for many years, and then we find it and someone's paying you to clean it up. How do we do it? Well, chances are good that we're going to use activated carbon adsorption columns. And it's a pretty standard process to have 2 columns, and one is doing the majority of the separation, and you have a meter between them to detect if any of the problematic compounds are coming through. And as soon as they start coming through a little bit, you're going to know that you have to take that one offline, go replenish or replace the activated carbon, and you can actually typically switch so that now the one that was in the second place is now in first place, and you sending through the new one as the backup. That all happens very quite routinely because we have a lot of these underground storage tanks. So if we're pumping up groundwater and treating it for that, that's pretty standard. And that would be technically a wastewater, I guess, cleanup, but it falls nowhere in this picture, right? So there are many processes that we might have for water or wastewater treatment that aren't necessarily tied exactly to these 2 systems. Maybe we do something to remove ammonia, and that could be some industry and not associated with a wastewater plant, right? So like a ammonia stripping or something like that. So we will talk about some things that are not necessarily typical in a plant like this, but here's a good overview of the typical design. Okay, let's take a quick look at Moodle, the page I've got set up so far before I let you go, but I am keeping it a little simple today, in part because my own voice is going to need it. I teach another course, the undergrad version, essentially, well, it's undergrad version of water and wastewater treatment in general, so we do cover some biological topics there at noon on Tuesday, Thursday. So for you guys, I apologize if my voice ends up a little shot. Today, keeping both a little simple, so hopefully it's all right. Okay, so we have our course here. In the intro, you see I've got the syllabus here. You'll find the YouTube playlists. Like I said earlier, if you go onto our page, even if I haven't tagged it over into this playlist linked here yet, it'll still be on the YouTube page generally, so you could follow this link and then go to the live section and find it. If I haven't uploaded or haven't tagged it appropriately yet, I think I forgot, and I actually have probably the book here for you.
It's easier to access it.
Yeah, so I think that's the textbook. I'm not. I guess I think I'm allowed to do that with the library, but don't tell on me if I'm not supposed to do that. The intro slides, I think I forgot to update these before class, so these are slightly outdated. I rearranged a thing or two, I think. But I will save over this intro PowerPoint with what we just talked about. So that'll be my routine thing to do, is save over whatever it is that we were just talking about. So on Thursday, I will update the first set of lecture slides and make that visible to you with a blank copy, and then we'll go through it and so on. So feel free to bring a laptop and take notes in class if you'd like to, in that manner. I have a section for assignments and exams. I think all of it should be hidden from you for now, but I'll post things as we go with the different exams. In the past, I have occasionally given take-home exams, so I'll get your feedback if you are interested in that or disinterested in that. At the moment, I think the syllabus is written for in person, but with your consent, I might do take-home at some point if that makes more sense. Okay, I think that's about it. Any questions or concerns? All right. Well, I'll see you guys on Thursday, and we'll get into some more technical stuff.